Okay, so welcome to today's. All right, hello, welcome to today's class. We're gonna get started. Okay, so we have the usual smaller collection of diehards here today during the exam week. So thank you all for coming. Everyone else, obviously, if you're not here, try to get caught up on your own. And we're going to cover today, we're going to continue on with the first couple chapters, 4 topics. We got a good start on VSEPR last week, which is the approach that we're going to use to convert a Lewis structure into 3-dimensional shape. And so we're going to finish that off today and then talk about molecular polarity, which is something that you can predict once you know what the shape of a molecule is and some other things about it. All right, so we're going to go into now 5 electron groups. So quick recap of last time, we covered 2, 3, and 4 electron groups and talked about how the total number of electron groups around the central atom dictates the arrangement of all of them into one of 5 basic shapes. And then depending on how many lone pairs there are, that's going to dictate what the actual molecular shape would be, which is just the arrangement that the atoms themselves make up. Now, when we go to 5 electron groups today, this is the one that in some ways is the most complicated of the 5 possibilities we're going to talk about. And so let's go back to that simulator that I'm going to have to load and close a million times because. All right, so we have back to here. Again, I encourage all of you to play around with this on your own time. It's very good, very useful. Okay, so we're going to go back into here and we're going to put in 5 electron groups. So that's 3, 4, and 5. Now, if we look at what this one looks like, it's not too hard to visualize the shape. So what you basically have are 3 of the atoms here, here, and here, if you can see the highlighter, okay? Those make up a triangle, and then you have one sticking up above the triangle, one sticking up below. So if we turn this on its side, you'll be able to clearly see that there's 3 of the 5 atoms make a flat trigonal plane, just like trigonal planar does, but then the other 2 atoms go above and below that, perpendicular to that triangle. So that's what it's looked like, and if you have good eyesight, you can see that it's called trigonal bipyramidal. And once again, if all of the electron groups are atoms bonded to the central atom, the molecular geometry is the same, also trigonal bipyramidal. Now I'm going to stay here in the simulator and just do all these for now because it's and I'll go back to the notes in a little bit because it slows me down if I keep this open. And so that's the situation when there's 5 electron groups. All 5 of those groups are going to adopt this shape. Now the question that's a little bit more tricky to answer with this electron group arrangement is where do the lone pairs go? So when you have one or more lone pairs in the central atom, you're going to take out one of these atoms and replace it with a lone pair. It's going to still maintain the same basic shape around the central atom, but where do they go? In the first 3 that we covered last time, linear, trigonal, planar, tetrahedral, all the positions are equivalent, and we can just put the lone pair wherever we please. The difference here is that there's 2 non-equivalent positions. There's the three atoms that are in the triangle. Those 3 positions are 120 degrees apart from each other, 90 degrees apart from the one on the top, and then the ones on the top and bottom are 90 degrees apart from all 3 of the ones that are nearby in the trigonal plane. So the question is, what's the better place to put the lone pairs? Lone pairs are more strongly repelling, so we want them to be further away if possible. And it might not be intuitive, but the way that you can easily remember this is that whenever you have 5 electron groups in this trigonal bipyramidal arrangement, however many lone pairs you have in the central atom, all of them go into one of these 3 triangular positions. So if we take out one of those and replace it with a lone pair, what you'll see, it reoriented everything, which is annoying, but when we put it back into where it was before, you can see that that lone pair goes onto one of those 3 positions that's in that triangular plane, okay? Now, if we have more than one lone pair, they all go there. So a second lone, and we call this seesaw. I'll draw it out and describe it a little bit. If you want to see why this is called seesaw, you put it this way. And a seesaw is synonymous with teeter-totter. I don't know what word they use for that here in Texas. We usually call it teeter-totter back home, but you can see it's rocking back and forth like that. That's why we call it seesaw. Again, best visualized in sort of this orientation. But the point at the beginning that I want to make sure we're clear on with with this is that anytime we put lone pairs into this, we're going to have them going on the triangular part. So 2 lone pairs now, again, they both go into that trigonal plane. So 2 of them there in the trigonal plane, the other 3 positions occupied by atoms. And those 3 positions are now going to be referred to as T-shaped. Again, rotated over, you can see that that's roughly the shape of a letter T. Just again, the molecular shape or the molecular geometry just accounts for the atoms themselves, ignoring the lone pairs. So you make a T-shaped with those combinations. And then we do have the possibility, it's a little bit more exotic, but it does happen, of having 3 lone pairs around the center atom with this electron group arrangement. So if, again, all 3 of the lone pairs in this case would occupy the trigonal plane. And then when you have 3 atoms left, your only 2 possibilities are linear and bent. And because the 2 atoms that are left are exactly opposite each other, 180 degrees, this would be an example of linear geometry. Okay, so those are the possibilities we have with that one. I don't think you can go any higher than that. Nope, that's the most you can do. Oh, unless you do more, but we don't really have any molecules like that, so forget it. It lets you do more, but that's as high as we're going to go, would be the AX2E3. All right, so let's go back to the notes and summarize all of those then. All right, so again, what we said is that whenever you have 5 electron groups, the arrangement of those electron groups is going to be referred to as trigonal bipyramidal. And then when you have 5 electron groups and all of them are atoms, so if you had an AX5 geometry, we would again draw that out in this way. So there's 2 ways of drawing this. I guess I'll give them both. So one of them uses the wedges and the dash we talked about last time. So you have the 2 that are coming above and below, and then you'll have a triangle that you can draw like this. Sometimes it's easier to visualize if you actually explicitly draw out the triangle. So we'll put the center atom here at the middle of a triangle. And then again, this would be trigonal planar, but then you have in trigonal bipyramidal, you have one coming out of the triangle on each direction. And if it's AX5, all 5 of those positions are bonded atoms. So as we always saw, if you have a certain electron group arrangement and all of those electron groups are are bonded atoms, then the name of the molecular geometry is the same as electron group arrangements. This would also be called a trigonal bipyramidal geometry. Now, the key difference here with this one and the other ones, which we kind of hinted at a little bit in the description earlier, is that we no longer have all of these positions being equivalent to each other. And you can kind of see that by looking at the different bond angle possibilities. So within the trigonal plane, all 3 of those atoms that are in the trigonal plane are still going to be 120 degrees apart. We saw that 120 degrees was the angle for trigonal planar. So there's going to be 120 degree bond angles in there in the trigonal plane. But then what you also have is these angles here, the angle between one of the apical positions, as we call it, one of the top or bottom ones, and the neighboring atom in the trigonal plane. And those would be exactly 90 degrees. So this is the only electron group arrangement where we have 2 different bond angles to consider and to remember. Okay, so it's 120 degrees from the 3 that are in the triangle, 90 degrees for the bond angles between those and anything that's in the top or bottom position. Okay, so that's called trigonal bipyramidal. And then as we showed in the web simulator that I was just in before, in all the rest of the possibilities that have 5 total electron groups, so the first one being AX4E, we're going to just replace one of these X's with a lone pair. And in this electron group arrangement, it's always advantageous to do that in one of these triangular positions. So for AX4E, it's still going to be 5 total electron groups. So we're going to have that same basic arrangement. But then one of those is a lone pair. It's going to be one of the 3 that are on the triangular positions has to be the lone pair. And that one is AX4E. Now, this is one that people tend to mess up a little bit, as it turns out. I don't know why. This is even when I review this topic in advanced classes, this is always the geometry that people flub for some reason. So I'm warning you about that now. We call it seesaw, as we said. Easiest to see that if we were to turn this over on its side. And then in terms of bond angles, again, because of this lone pair sort of pushing everything over a little bit more strongly, you're going to be similar. You still have this one here, but that's going to be a little bit smaller than 120 degrees. And then this one here, a little bit smaller than 90 degrees. So Again, we can't predict how much smaller very easily, but a little bit smaller than 120 for that remaining bond angle between those two, a little bit smaller than 90 for the other ones. So still based on the same numbers, but a little bit compressed because of the lone pair. All right, so that's AX4E. And then when we go to AX3E2, again, still 5 total electron groups. 3 plus 2 is 5. So they're going to arrange themselves in this way. Triangle with one above and one below. Now we need 2 lone pairs there. And as we said, all of the lone pairs in these electron group arrangements, however many we have, 1, 2, or 3, is going to go in one of these positions. So it doesn't matter which 2 we pick, but if we put them in there, that leaves those as the X's. And again, to turn this over on its side, you see it better, but this is called T-shaped. This time we only have 1 bond angle because we lost 2 of the 3 positions on the triangle. So this one doesn't have a 120-degree angle anymore. Bond angles are always defined between atoms, not between atoms and lone pairs. So you're going to just have this bond angle here and the same one on the bottom, which is going to be a little bit less than 90 because of the influence of the lone pairs. Ideally 90, but a little bit less because of the lone pairs that are pushing these ones over a little bit. And then finally, AX2E3. The formula of this compound only has 3 atoms in it. So as we said last time, the only 2 possibilities are going to be linear or bent. So if you see a formula that has 3 atoms in it, you have a 50-50 chance of getting it right if we're asking you for molecular geometry. Linear or bent in this case. And then if we go to this, what we said, again, all the lone pairs go in the triangular positions. So never put a lone pair on the top or bottom. So that leaves those 2 atoms exactly oriented opposite each other, above and below that now invisible triangular plane that only has lone pairs on it. But that gives us a linear geometry. And in this case, the bond angle is exactly 180 degrees. Not less than that, because you have 3 lone pairs, but they're pushing up on this atom and down on this atom the same, so they don't compress the angle at all. They're basically all those repulsions cancel each other out, and it's still best to have these 180 degrees apart. So exactly 180 degrees anytime you have a linear geometry. Okay. So those are the 4 possibilities for 5 electron groups. And again, it's the one that is sometimes the most complicated, in part because there are 4 possibilities. None of the other ones have that many possibilities of different combinations of X and E. And again, because the positions are not equivalent, so you have to remember that you always put the lone pairs on the triangular plane, and the names of some of these shapes not always intuitive unless you rotate things around. So any questions on those? Any of those that you want to see again in 3D, let me know. Yeah. This one, the dashed lines tell you when we draw a structure like that, it's telling you that that bond is kind of going away from you into the plane of the page. So it's trying to indicate 3-dimensionality to it. If you prefer, again, you can always just draw the triangle in. That's a perfectly valid way of doing it. But it's showing you that this one bond here, and the number of dashes is irrelevant. Anytime you draw a bond with dashes, it should be more wedged than I'm drawing it. It's not. I'm not doing a very careful job. Maybe more like a wedge shape like that is maybe a little bit more accurate. But nonetheless, it typically indicates that that bond is going away from you. So imagine it's protruding into the board. That's how we often indicate things when we need to include 3 dimensions in our drawings. No perfect way of doing it, but that's how it's often done in chemistry. But again, for this one, especially if you like to just visualize it better with the triangle drawn in, go ahead. There's nothing wrong with that. You'll see it both ways. Yeah. Yeah, so for all of these, the electron group arrangement would be trigonal bipyramidal. The electron group arrangement only depends on how many total electron groups there are, and there's only 5 possibilities. The names that I gave below each of them are the molecular geometry, which is the same if there's no lone pairs, and then you have a different name for that if one or more of those positions is occupied by a lone pair. Yeah. Not with 5 electron groups. So we saw bent geometries when you had either AX2E or AX2E2, because in that case, the native electron group arrangement had bond angles that was either 109.5 or 120. And if you just replace 1 or 2 of those with a lone pair, you're left with those being at an angle to each other. But in this particular geometry, because you're occupying those three positions with lone pairs, and you have to do that to minimize electron-electron repulsion. That leaves the remaining two atoms 180 degrees apart. So with 5 electron groups, that's how it would always be. So one other hand up, but maybe that person changed their mind. All right, we will move on to the last one now. The highest that will go, 6 electron groups. And so again, going back here might be helpful to start with. Yeah, so there's 3 possibilities with 6 electron groups. And again, I have to keep reloading it if you were paying attention because it slows down my computer. So 6 is as high as this lets you go as well. See, it's now grayed out. I can't do any more than that. It's not the limit of nature. There are things that have more than 6 electron groups, but not what we'll talk about here or in the context of either. Okay, so anyway, what this one ends up being, the name is a little bit counterintuitive. It's octahedral. Octa, like, oh, that means 8, but there's only 6 things around it. Why do we say octa? Well, that's because if you drew a triangle through each of the 3 neighboring atoms, so 1, 2, 3, if you do triangles, so there'd be 8 triangles that are surrounding that shape. I think maybe I have a graphic of that on the slide, perhaps, but I'm not sure if I did. But it's called octahedral, but there's only 6 electron groups. And again, the easiest way to visualize this is with, you have a square, so 4 atoms that make a square, and then one above and one below the square. So a flagpole coming out of the square and a flagpole going down below it. So that gives you what's called octahedral. Now, it turns out in this electron group arrangement, all 6 of these positions are equivalent. So again, 5 electron groups is the only time when you have to worry about different positions not having the same bond angles and things. In this one here, every atom is mutually 90 degrees apart from every other nearest neighbor from it. Okay, so all 90-degree bond angles in this native geometry here, in all positions that are exactly equivalent. So then what that means is if we put one lone pair on, so if we have AX5E, where we replace one of these atoms with a lone pair, it doesn't matter which 6 of those positions we choose for the lone pair. They're all exactly identical to each other. So electron-electron repulsion will be the same for all of those. So if we do that here, we take off one and put a lone pair in. Again, it puts it in a random place, but it doesn't matter where. Now, the best way to visualize this geometry is to put the lone pair on the bottom, as it turns out. And so when we do that, we would call that square pyramidal. So it's a square base, 1, 2, 3, 4. Sorry, the pen's not working. 1, 2, 3, 4 in the square base, and then just one now coming above that square. So we call it square pyramidal. The lone pair does sort of fold it up a little bit like an umbrella, but again, a very small effect, not a huge difference. So we call that square pyramidal, still an octahedral arrangement with 6 total electron groups, but the geometry will be called square pyramidal. And still bond angles that are close to 90, a little bit compressed because of the lone pair. Now, the only slight difference now with this one is if we have 2 lone pairs, it doesn't matter where we put the first one, they're all equivalent. But lone pairs, as we said, repel more strongly than bonding pairs. So if we have 2 lone pairs, we want to make sure that those 2 are as far away from each other as possible. So a second lone pair would always go exactly opposite the first. So again, wherever you put the first one doesn't matter. But if you have 2 lone pairs, they have to be 180 degrees apart from one another. And that leaves the remaining 4 atoms forming a perfect square. So we would call that square planar. I had a cantankerous, let's say, grumpy professor in graduate school who was like, why do they call it square planar? Have you ever seen a square that's not a plane? So he just likes to call it square, but he's the only person I think in the world that does that. So you'll typically see square planar as the name that you'll use, but it's, again, just 4 atoms in a square. And if you go to the side view, you can see that it's totally flat. Okay, with 1 lone pair above the square, 1 lone pair below. But again, the shape that we would describe for those remaining atoms is square planar. All right, so again, play around with the simulator to help you learn these. I don't want this to be an exercise in memorization, but I think in chemistry in general, visualizing things in 3 dimensions is important. All right, so now to just draw everything out, AX6, anytime we have 6 electron groups total, we would call that an octahedral electron group arrangement. All right, and then the first of those 3 possibilities is AX6. All 6 of the positions are atoms. So there's, again, 2 ways to draw this. Sometimes the more intuitive way is to actually draw out a square. So you have a square with 4 atoms around the center atom, 4 X's in this case. And then octahedral puts 1 above and one below the square. I should draw that a little bit better like that. Again, all the same distances, so I didn't do a perfect job, but they should all be the same bond distances, all the same angles, 90 degrees. The other way to draw it is with the dashes and the wedges. So again, these two bonds that are drawn as solid wedges, sometimes shaded in, sometimes not. You'll see it both ways. Those indicate two bonds that are coming towards you out of the plane of the page. These dash wedges, as was clarified by the question earlier, indicate atoms going away from you. So that makes a square that's sort of perpendicular to the page, and then one above and one below. So there's, again, two ways of drawing this. And you have to, it's helpful to visualize. So that's where the simulator is very useful for visualizing. And so we're going to call that, again, in this case, the molecular geometry is also octahedral. Whenever all of the positions are occupied by atoms, the electron group arrangement and the geometry have the same name. And the bond angles in this case are exactly 90 degrees. The 4 on the square, that's obvious, and then one above, one below that are perpendicular to that. If we go to AX5E, it's still going to be an octahedral arrangement. So there's still going to be, actually, let's not put X's in yet. There's still going to be everything arranged in that same way. But now one of those 6 positions is a lone pair. It doesn't matter which one you choose, but to visualize the geometry most clearly, I like to put it on the bottom. That leaves the rest of those as X's, and then hopefully it makes it clear why we call it what we do, which is square pyramidal. So there's still a square base, but then this time only one atom above. So I think somebody correct me if I'm wrong. I think the famous Egyptian pyramids are square pyramids. I think they have square bases and come to a pyramid. I don't think they're triangular pyramids, but anyways, so it's a pyramid shape. Again, 4 on the bottom, and then one that caps them on top, with one lone pair also there. But again, we don't consider that when we're naming the molecular geometry. Bond angles get compressed a little bit because of the lone pair. Again, we can't say how much, a little bit less than 90. Basically, this one's pushing up on the 4 atoms in the square plane, starts to fold up a little bit like an umbrella, and shrinks those angles by a little bit. All right, and then if we go to the last possibility with 6 electron groups, that's where we put in 2 lone pairs now. And there is none that has 3 lone pairs for this one, so this is the last one. We again start with an octahedral arrangement. And then 2 of those 6 positions now have to be lone pairs. Now, there's different possibilities for which 2 you choose, but the important thing is they have to be 2 positions that are 180 degrees apart, as far apart from each other as possible, to be able to minimize electron-electron repulsion. So putting it on the top and bottom here is helpful, because then you can see that the rest of the 4 atoms occupy a square. And we call that, again, to be a little bit redundant, we call it square planar, emphasizing that it is a totally flat planar structure. There is another way to draw this, which would be just to draw it in the plane of the page itself, like that. In this case, you can't easily indicate the lone pairs, but there would be an understanding that there's one lone pair shooting out towards you, one lone pair going back away from you. And the rest of the atoms that we look at occupy a square with exactly 90-degree bond angles in this case. You have a lone pair above and below that are both pushing equal and opposite to each other, so no distortion in that there. All right, so that's the end of VSEPR. So any last questions on just the basics of that? All right, so now we're going to go forward and cover a few subtle things that you can that you can make predictions about with VSEPR. One of those is bond angle compression. Now, we've already discussed as we've gone through these different possibilities that anytime you have lone pairs in the structure, that would tend to compress the bond angles, except in those rare cases where there's 2 or 3 of them that basically cancel out. But in most cases, lone pairs on the center atom cause bond angle compression. Can't say how much. But then the other one that, again, we're going to not give a lot of details on this, but just to be aware of a little bit, is that if you have double bonds or triple bonds in the structure, those can distort bond angles as well. And that's because a double bond or triple bond, instead of having just 2 electrons in it, one pair of electrons is now 4 or 6 electrons occupying that bond. So it has more electron density, so it has more repulsion with other things around it. So as an example, if you have this structure, this is a better one. Let's do this one here with carbon. All right, so yeah, this is called formaldehyde, if you've ever heard of that term before, just COH2. So that's the structure. And if we drew the Lewis structure, that's what we'd come up with. There's also some lone pairs on the oxygen, which don't really factor in because we're just focusing on the center atom for this approach. But if you look at this structure here, it's formerly AX3, although there's two different outer atoms, but it's AX3, no lone pairs on the center atom. So you would still predict trigonal planar, and by and large, it very much is trigonal planar. But again, the double bond here on oxygen has a little bit more electron density than the CH single bonds. So your prediction, at least, it doesn't always work out this perfectly because there's other factors that you sometimes can't easily account for. But the prediction here is that because of this double bond repelling a little bit more strongly, it's going to sort of pinch those two hydrogens together. So you would have this bond angle being a little bit less than 120 degrees, this one being a little bit bigger than 120 degrees by virtue of that. All right. And so that can happen with double bonds, triple bonds. And it's not an effect we're going to talk about in great detail, but even though from the standpoint of VSEPR, we don't really care whether it's a single, double, or triple bond just from naming or predicting the structure, those double or triple bonds can have at least small effects on the observed bond lengths, even though we would still call this trigonal planar. It doesn't affect the geometric outcome. It just affects the angles a little bit. But the important thing to remember in all of this, if you're trying to make predictions about how are bond angles perturbed, the lone pair repulsion is the strongest. And so that's why, again, when we did the last example, square planar, we had to put the two lone pairs 180 degrees apart. Those are the strongest repelling. Anything that involves lone pairs is going to repel more strongly. And you want those to be as far away as possible. And lone pairs are going to thus have the biggest effect on the geometries. So that's not a huge topic for us, but something we should be at least a little bit aware of. The more important thing is let's practice this approach and see kind of the typical things we would ask you to do. So obviously one of those typical things would be to just give you the formula of a compound and ask you to predict what would be the electron group arrangement and or the molecular shape or geometry. Molecular shape, molecular geometry are interchangeable. So that's what we do. Very often that's how it's going to be set up for you. So as a useful review for the exam this week, if you haven't taken it, this is always going to start with a Lewis structure. We can't make any predictions about VSEPR, about the shape or anything else related to that, unless we know what the Lewis structure looks like first. Because again, we're going to classify this on the basis of how many atoms are bonded to the center atom, how many lone pairs the center atom have. We can't just get that from the formula. We know already that there's 3 atoms on the center atom. PCl3 tells us that it's AX3 something, but we also have to know how many lone pairs there are to be able to correctly predict the electron group arrangement and the shape. So we have to make sure we do that. It turns out for VSEPR, you don't have to get you don't have to worry about like formal charges and double and triple bonds nearly as much, but you do need at least a decent Lewis structure to get started. So if we do that for this one, PCl3, we have to count valence electrons first to be able to draw a Lewis structure. So if we get the periodic table up, phosphorus is group 5, so there's going to be 5 valence electrons from phosphorus. Chlorine is in group 7, so each chlorine will provide 7 valence electrons. So we have to count that up first to get our Lewis structure. 1 phosphorus with 5 valence electrons. I think we did this one, but I'm just going to do a quick review of it in case you've forgotten some of these steps. 21, so we have 26 total valence electrons. I think we did draw this out in the lecture where we covered Lewis structures, so you've seen it before. So when we draw this out, we get 3 single bonds to chlorine. We complete their octets with 3 lone pairs each, 6 more electrons each. So now they have a total of 8 around them. 3 octets is 24. The total we have available is 26. So the last 2 go on the center atom as a lone pair. We don't need any double bonds in this one. We shouldn't have any, but you don't have for VSEPR, you can certainly just stop here. It follows the octet rule, and there's no formal charges anyway. We don't have to worry about that for VSEPR. So then from there, we just have to classify the geometry using the AXE notation. Center atom, 3 outer atoms, so AX3, that you can tell from the formula, PCl3. But then the important part is we use the Lewis structure to tell us that there's also 1 lone pair in the center atom, AX3E. So because there's 4 total electron groups, the electron group arrangement would be tetrahedral. And then one of those four positions is a lone pair, doesn't matter which one. And that leaves PCl3 looking like this. And the name for that, which is what this problem would have asked you for, not to draw it yourself, but to name it, is trigonal pyramidal. All right. So it's three of those occupying the base of the pyramid. The central atom is sort of the apex of that pyramid. So trigonal pyramidal is the correct name for the molecular shape. Tetrahedral would be the electron group arrangement. And again, you have to at least have a mostly complete Lewis structure to be able to make those predictions. So make sure you learn how to do that. Make sure you don't forget it if you already have, because it is going to be used a lot in this chapter as well. All right, questions? Yeah. In this one, no. So in tetrahedral, when there's four total electron groups, all four of those positions are 109.5 degrees apart. Now, we're not actually going to ask you guys to draw anything because that's beyond the limits of what WebAssign can allow you to do. But if you were drawing it yourself, it wouldn't really matter. I put it on the top because it makes the name of the geometry much more intuitive, but all of them are the same, so it doesn't matter. So then we're going to go on to just some other ones. Let's do carbonate, CO3 2 minus. So again, sorry, I'm a little bit disorganized my notes here. Here we go. All right, so for CO3 2 minus, we'll again start with a quick Lewis structure: carbon, oxygen, and a 2 minus charge to account for in the electron total. All right, we've seen these a lot already, but carbon is group 4 valence electrons. Oxygen group 6 valence electrons. So that's how we're going to total those. 4 from carbon, 6 from each oxygen, but there's 3 of them in the formula. And then 2 extra electrons because of the 2 minus charge. So 24 electrons total. All right. So then we have to put 24 valence electrons around our center atom. We start with single bonds. We complete the octets of each of those oxygens with, again, 6 more. Now, at this point, we have used up all 24 of our valence electrons. We've filled up 3 octets on the 3 oxygens. 3 times 8 is 24. There's no left. So nothing for the center atom in this case. Now, what we should recognize at this point is that, well, okay, the center atom doesn't have a complete octet and carbon should. So there should be one double bond. There's going to be resonance structures here. So, you should be familiar with those topics from the standpoint of what we asked you to know for chapter 3. It is important nonetheless. But for this point purpose, we could just stop here. I mean, again, the correct Lewis structure should have a double bond to complete the octet. And there would be 2 additional resonance forms that you can draw where you move the double bond around. All that stuff is still true. From the standpoint of VSEPR, though, if we're just asking you for the molecular shape, whether you stopped here with an incomplete octet or did what you're supposed to do and draw in a double bond, you'll make the easy prediction that this is AX3 structure or AX3E0, sometimes how it's written. But the important part is no lone pairs in the center atom. Doesn't matter whether double bonds are there or not. That's always true. And so AX3E, the electron group arrangement and the molecular geometry would be called trigonal planar. That's one where you just put the 3 things into a flat triangle, 120 degrees apart. And so that's the correct shape for carbonate, CO3 2 minus. So again, you need a mostly complete Lewis structure, but details like double bonds and resonance structures don't really matter for VSEPR. All right. And then just probably one more, I think. Xenon tetrafluoride. We haven't talked a lot about noble gases yet, but we call them noble not because they have a royal title or anything, but because noble in this case means inert, or sometimes they're called inert gases. They don't react with anything. But there are some rare compounds out there that involve the noble gas as a central atom. So these xenon fluorides are one of them. So XeF4, there's also XeF2, or 2 fluorides of xenon. And so again, to get the molecular shape, we're going to follow the exact same approach. We're going to draw a Lewis structure and then use the AXE notation to predict what that means about the electron group arrangement and or the shape. So the periodic table here, all the noble gases, including xenon here, are in group 8. So that's going to bring in 8 valence electrons, S2p6 valence configuration. And then each of the fluorines from group 7 will contribute 7 valence electrons. So we'll count them up in that way. 8 electrons from xenon, 7 from each fluorine, this is going to give us a total of 36 valence electrons around the central atom. So when we arrange those, we're going to still start the approach the same way. Single bonds to fluorine. Complete their octets with 3 more pairs each, 6 total. All right, so then what we look at is we have 4 complete octets on fluorine. So 4 times 8 is 32. We add 36, so we have 4 more left. Those are going to go on as lone pairs on the xenon. So our central atom in this case has 4 lone pairs. Sorry, 4 atoms and 2 lone pairs, AX4E2. And the X4 part comes from the formula, but we had to draw the Lewis structure to figure out the E2 part of that. 6 total electron groups, so they're going to go octahedral. And then 2 of those are lone pairs, as we just talked about as the last example. They have to go 180 degrees apart. Oh, sorry, the rest of those are all fluorines. We're getting too crazy with lone pairs here, sorry. The rest of those are all fluorines. And as I said, we call that square planar. All right, so that's a pretty uncommon geometry as it turns out for a main group molecule. This is one of the only examples of square planar that you'll come up with. All right, any questions on that? Yes, sir. Well, in this case, it wouldn't be, only because there's 3 identical resonance forms. So that double bond is actually delocalized. So if you drew them all out, you'd have the double bond here, here, or here. All 3 of those kind of average together to give you the total structure. And so it's really that each of those carbon-oxygen bonds is 1 1/3 bond order. They're all the same. And so in that case, the bond angles will still all be exactly 120 degrees because they're equivalent. If the double bond is localized in one position, then it would compress the other angles. But you would still call it trigonal planar nonetheless. It wouldn't change the name. It would just change the angles potentially. All right. Good question, though. So then the last thing I have for just the VSEPR part is a quick summary. Again, I don't want this to be an exercise in memorization, but this table here summarizes everything in terms of different, the steric number possibilities, and then the different geometries that come from different combinations of AXE that you can have. Again, keep in mind that for this column here, where there's no lone pairs on the central atom, the electron group arrangement and the molecular geometry are the same. For the rest of these that involve lone pairs, they would have the parent electron group arrangement that's determined by the steric number, but then they would have different names for the molecular shape, which are also given here. So helpful table to maybe get you oriented as you're getting started. Again, you're not going to have the table on the exam, so you need to internalize this. And I think I encourage you to approach it more from the standpoint of learning how to visualize the structures, and especially just learning these sort of 5 parent arrangements and then building off the rest from there and being able to use that to clue you in as opposed to just brute force memorization. But however you choose to learn it, this is really a summary of all the information you need on VSEPR. Now, the next major topic that this chapter covers, which stems directly from this, is molecular polarity. Now, we already talked about polarity in the context of an individual bond. So if you have 2 atoms bonded to each other, we mentioned how the electronegativity values of the 2 atoms are going to determine whether or not the bond is polar. How different that electronegativity is going to determine how polar it is. And so that's kind of things we've already covered again back in chapter 3. So just as a review of that, your dipole, your negative charge, your partial negative charge is sort of oriented towards the more electronegative atom. So for example, we gave this one before. If you have an HF bond, fluorine is very electronegative, hydrogen not as much. So you would have a dipole that's pointed towards fluorine, which can be indicated here as sort of a vector arrow pointing towards the more electronegative atom. A slightly more intuitive way to do it from the chemistry standpoint is just with partial plus, partial minus charges. Again, indicating that this is not an ionic bond. The electrons are still shared, but more of that electron density is slanted towards the fluorine. And that's what it means for a bond to be polar. And how polar the bond is, as we said, depends on the difference in electronegativity. So if you're ranking the polarity of all of the carbon-halogen bonds, carbon-fluorine has the biggest difference because fluorine is the most electronegative. Carbon's electronegativity is about 2.4. Fluorine is 4. And then carbon-chlorine is a little bit less polar because chlorine is less electronegative than fluorine, so the bond is less polarized, and it goes in that sort of order. So these are some things we would expect you to have sort of learned back in chapter 3. Carbon iodine is approximately nonpolar. The electronegativity values of carbon iodine are almost the same. Okay, but not a little bit polarized, but almost nonpolar. So that's the magnitude of the polarity. Now that's kind of how we would evaluate the situation for just a single bond, two atoms bonded to each other. But how does it work if we're talking about the polarity of an entire molecule? Because in the molecules that we're talking about that have more than two atoms in them, you're going to have possibly more than one dipole moment for each of the bonds. And how do they sort of combine with each other to determine the polarity of the entire molecule? So the definition of molecular polarity is whenever you have an uneven distribution of charge over an entire molecule or a large part of it. So when we're talking about molecular polarity, again, we're not just thinking about the polarity of two atoms bonded to each other, but we're thinking about the distribution of electrons over the entire molecule, which we're talking about situations now where there's 3 or more atoms involved. So we're talking about the distribution of charge over a whole molecule or a large part of it. We're not going to talk about this from the standpoint of anything quantitative, so you don't have to worry about like learning this number or any calculations you're going to have to do. But there is a way of measuring polarity and kind of quantifying it. Again, we can qualitatively say this is more polar or less polar based on differences in electronegativity. There is a numerical and measurement-based approach to it, and you use a unit that's called the debye. It's a compound unit named after somebody with capital D. And what that number is 3.34 times 10 to the minus 30th coulombs times meters, where coulomb C is the unit for charge, meters is the unit for distance. So the dipole moment of something, how polar it is a function of how much charge is separated and how large of a distance those charges are separated over. Again, we don't have to worry about that too much, but that's how we would measure it. And again, the physical quantity that we're measuring is called dipole moment. Which is abbreviated with Greek letter mu. Now, again, even though there is a quantitative basis to this, we don't expect you guys to know this part of it. This is just background. The determination you're going to have to make for what you do in this class is basically just a binary decision. Is a molecule polar or nonpolar? If it's polar, that means it has a dipole moment. If it's nonpolar, that means the dipole moment is 0. And that's the distinction you're going to have to be able to make on the basis of the electronegativity of the atoms and the shape of the molecule. Both of those come into play. Okay? So let's talk about the different possibilities then that you can have. Now, the first thing is that if a molecule is going to be polar, the bonds in that molecule have to be polar. That's not enough of a criterion by itself, but you need to have polar bonds. So some things, just by looking at the formula of the compound, you can already tell that it's going to be nonpolar, even if you don't know what its shape is. So these would be called homoatomic molecules. These are molecules that only have one atom in the formula. So dinitrogen N2, the natural form of phosphorus is P4S8. In these cases, you have the same atom bonded to itself, so there's no electronegativity difference. There's going to be no distribution of no unequal distribution of charge. So the bonds are perfectly covalent, electron density perfectly shared all around. Okay, so in those cases, just by looking at the formula of the molecule, without even considering what its shape would be, you can know that it's nonpolar. You might want to be aware, I don't think it's going to come up. One exception to this is ozone, O3. Probably heard of the ozone layer in the atmosphere. Even though O3 is all oxygen, if you draw the Lewis structure of O3, you have formal charge. You have no choice but to have formal charge if you want to complete the octet of all three atoms. So you'd have a partial negative and a partial positive charge in there. So that makes ozone polar. But that's the only exception I can even think of off the top of my head. For all the rest of these polyatomic molecules that have just one type of atom in them, you already know from the formula that they're nonpolar. So that has to be true. So these ones are not polar. Now, but then beyond that, in the cases where you can't just look at the formula and tell, you have to also consider the geometry. So if there's more than one type of atom in the formula, you have to look at the geometry as well as part of it. And so again, the idea is that the presence of polar bonds, so just because the bonds are polar doesn't mean the whole molecule will be polar. So we'll give some examples, but there are many examples. It's a very common situation to have a molecule where all the bonds are polar, the individual bonds are polar, but basically those polarities all cancel out and the whole molecule itself would be nonpolar. So again, in order to make that determination, you have to also look at the shape of the molecule, not just the electronegativity values of the atoms and the individual bonds. Okay. So let's go through a lot of different possibilities then. So this is, what I'm going to cover in class today is maybe not exhaustive, but it's going to cover the vast majority of possibilities that you will encounter in this class and the predictions that you have to make, and just some patterns that are helpful to recognize and remember. So the first one is that if you have a structure that has no lone pairs on the center atom, AXME0. Now this is true, again, the caveat here is that this is true if all of the X's are the same. Which means you have one type of outer atom, not two different things bonded to the center atom. In most cases, those would be polar because the dipoles don't cancel. But in this case, we're talking about structures where all the X's are the same. These will all be nonpolar. And again, so for those ones there, once you know that it's AX whatever E0, once you know there's no lone pairs in the center atom, you can confidently predict that it's going to be nonpolar without having to think about it more deeply than that. Now, why is this the case? And I don't want you to just memorize things. I want you to understand them. Let's go to the simplest example, which is carbon dioxide. So carbon dioxide, CO2, you would predict is a linear molecule, and there's no lone pairs in the center atom. So this is the structure. There's lone pairs in the outer atoms that we don't need to worry about in this case. But the linear geometry is the important part. Now, again, we can indicate the polarity of the individual bonds on the basis of electronegativity. Oxygen is more electronegative than carbon. So each of these CO bonds itself will be polar. So we would have a delta minus on that oxygen, a delta minus on that oxygen, and then really two delta plus on carbon because each of those bonds is polar. But if we think about it in terms of vectors, kind of like a tug of war analogy, you have one dipole pointing this way, another dipole pointing the opposite way, and those two dipoles completely cancel each other out because the two carbon-oxygen bonds are identical and 180 degrees apart exactly. So in that situation, the two dipoles, even though they're both polar, they cancel each other out, and there's no net polarity. So this AX2 molecule, or AX2E0, if it indicates there's no lone pairs, completely nonpolar. And again, you can't get that information just from the chemical formula. You had to work through to make sure that there is also no lone pairs in the center atom. The rest of these are not as intuitive, I would say, but it's always going to be true. So if you have BF3, which is AX3, this time you have three polar bonds. Each of the BF bonds is polarized towards fluorine. So you'd have to be good at, two-dimensional vectors to fully convince yourself of this, but you can still remember the pattern that this is, again, no lone pairs in the center atom, three identical outer atoms. This is also nonpolar. This time there's three bond dipoles. They all cancel each other out to give a net zero dipole moment, no dipole moment at all. And then even less obvious, but the same thing is true for carbon tetrafluoride. This time there's four atoms on the center atom, but no lone pairs. 4 dipoles, but they all, again, cancel each other out. This time it's three-dimensional, so not very obvious like it was for the first example, but all 4 of these bonds are exactly equal to each other in terms of their polarity. And with the arrangement of AX4 being tetrahedral, they all cancel each other out. All right, so you don't have to necessarily be able to rationalize that very clearly, and it is hard to do for anything more complicated than linear. But again, whenever you have an AXME0, AX2E0, AX3, AX4, AX5, AX6, if there's no lone pairs in the center atom and all the X's are the same on the outside, the molecule will be nonpolar. All right. Now, another common situation is a structure that has more than one type of outer atom. So we can still classify them with the AXE notation, but in this case, there's 2 or more different X's. They're not all the same. In most cases, these would be polar. Again, you can't really draw a lot of blanket statements on this, but typically for the molecules that we would encounter in this class, you could just pretty easily predict that they're polar. So for example, if we saw carbon dioxide last time, let's replace one of the oxygens with a sulfur to make, I don't even know what you call this, carbon monoxide, monosulfide, one of each, right? All right, so it's still linear, but this case, what you have is a very polar CO bond, big electronegativity difference between carbon and oxygen. But sulfur is less electronegative than oxygen, and the difference between carbon and sulfur is very small. So the dipole for this one is smaller. It's still pointed towards sulfur, but it doesn't completely cancel each other out. Because this time the 2 dipoles are not equal. In order for them to cancel each other out, they have to be equal and opposite in direction. This time the dipole pointing towards oxygen is stronger, and so you're going to have a net dipole in this molecule pointed towards oxygen. Partially canceled out by the sulfur dipole, but not completely. So there's still going to be an unequal distribution, and this would be a polar molecule. And then another common type that you'll see a little bit in this class, but especially if you go to organic chemistry, is AX X prime 3. I'll call this AX X prime, basically 2 different outer atoms, so X and X prime, but that's not important for us. But then if you go to like AX X prime, so a common one is chloroform, CHCl3. So this is tetrahedral, but there's 2 different outer atoms. One of them is a hydrogen, 3 of them are chlorines. We call this chloroform, not that you need to worry about that. And so in this situation, you have dipoles pointing towards each of the chlorine atoms. They're the more electronegative ones. And then you have a CH bond that is mostly nonpolar. CH bonds are pretty nonpolar. A little bit of a dipole towards carbon, but a pretty small one. But nonetheless, it doesn't cancel out with the other 3. So there's going to be a net dipole in this direction, and this molecule would be polar. Again, you don't have to perfectly visualize or understand that necessarily, but it's a structure that would be classified as AX4. There's no lone pairs in the center atom, but because there's 2 different outer atoms, hydrogen and chlorine, the prediction would be that it's polar. And again, in this course, there's going to be, I can't think of an obvious exception to this, but I put mostly polar just because I don't want to assume that it's universal, but you could pretty safely assume that. All right, and then another common category that you'll see, again, your job is going to be to decide if something is polar or not, so you don't have to think about it in more depth than that, would be structures with 1 lone pair on the center atom, I should say, to be more specific. These ones are always polar, no exception to that, okay? So a common example of this would be NH3. This is AX3E with 3 hydrogens, 1 lone pair on the nitrogen as well. Nitrogen is more electronegative than hydrogen, so you have dipoles all pointing towards it. But because there's 3 dipoles and the 4th position is a lone pair, they don't cancel each other out. So this is trigonal pyramidal, and this would be polar. Again, any structure with 1 lone pair is going to be polar. 1 lone pair on the center atom has to be polar. All right, and then another one would be SO2. This has 1 lone pair on the center atom. You need some double bonds to complete the octet and or minimize the formal charges. One or more double bonds to do that. But again, you have identical sulfur oxygen bonds, but because the dipoles are bent relative to each other, they don't cancel each other out. If they were linear, they would cancel out, but because they're bent, they reinforce each other and make this whole molecule polar. And a useful thing to remember also that's related to this is that all bent molecules are polar. All right. Again, with 3 atoms in the formula, SO2, there's only 2 possibilities, linear or bent. If it was linear, it would be nonpolar, like CO2. But if it's bent, it's polar, like SO2. And so that's another useful distinction. All right. And then really the last category you have to worry about are the structures that have more than one lone pair in the center atom. So again, if there's no lone pairs in the center atom, typically it's nonpolar unless you have 2 different outer atoms. If there's one lone pair in the center atom, it has to be polar. For these ones here, it's a little, they're a little bit more of the in-between ones. So these may or may not be polar. There's no easy prediction for these, so you have to kind of remember the different possibilities. There's not that many either. There's only, what, 4 or so with, I don't know, I forgot how many, 4 or 5 structures that have more than one lone pair, so it's not that bad. So they may or may not be polar. So some of them are. So as an example, if you draw the Lewis structure for water, H2O, again, this is another one that fits in that linear versus bent dichotomy, but this one is AX2E2. That makes it bent, and that makes it polar. Any bent molecule would be polar, as we said. All right. But that one has 2 lone pairs in the center atom. So again, there's no strict rule for 2 or 3 lone pairs. But then if we go to the one we just did earlier, xenon tetrafluoride, we saw that that one was square planar. A couple different ways of drawing it. But you would have 4 fluorines making a square plane. And then 1 lone pair above and below. And then if you draw this in the flat orientation, which I think is more useful here, you can see that all the dipoles cancel out. You have a dipole towards fluorine, but it cancels out with the one that's opposite to it. This dipole pointing right to left cancels out with the other one that's right to left to right. So all the dipoles have one that's equal and opposite in magnitude that cancel each other out. So this is an AX4E2 structure, again, one with 2 lone pairs again, but this one, it turns out, is nonpolar. The name of the geometry is square planar, and that ends up being nonpolar. So the point being that for structures that have more than 1 lone pair, there's some of each. Here with 2 lone pairs, this one's polar, this one's nonpolar. So again, you'll have both possibilities. So any questions on that before we do some examples? All right, so then just some example problems to wrap up the polarity. Determine the molecular shape of PCl5, and then determine whether it's polar or nonpolar. I'm all out of short sorts here. I can do this one on the top of my head. All right, again, that's the sort of level of depth we want you to think about, is just deciding if it's polar or nonpolar. Get from that page. All right, so PCl5, again, let's go through it from the start. We have to draw a Lewis structure first to be able to predict the shape, which is part of this question. And then also the shape matters for whether it's polar or not. All right, so phosphorus, we did PCl3 earlier, so it's the same elements, just different formula. So phosphorus is group 5, chlorine is group 7. So 5 valence electrons from phosphorus, 7 from each of the chlorines, and there's 5 of them in the formula. So 40 valence electrons around the central atom. So when we draw this one in Lewis structure form, we put all 5 around the central atom, single bonds. We complete their octets with lone pairs. All right, so at this point, I think I can't do math. Oh, that's right. 40 electrons. Okay. 5 octets around each of the chlorines. So that's 40 already. So we've used all 40. So no lone pairs in the center atom in this case. It stops there. So that makes it AX5E0. Now, from the standpoint of predicting polarity, we just said if there's no lone pairs in the center atom and all of the X's are the same, which is true here, it's PCl5, then we already know that it's going to be nonpolar. So that part we can answer without even considering the shape and what the name of it is. It's nonpolar. Now, this question also asks for what the name of the molecular shape is. So again, 5 electron groups gives us trigonal bipyramidal. I draw that a little bit better. And in this case, all 5 of them occupied by chlorines. So when you have no lone pairs in the center atom, in addition to the prediction that it's nonpolar, the electron group arrangement and molecular shape are the same, both called in this case trigonal bipyramidal. All right, so that just took it one step further from what we did earlier, which is just using the information about the shape to predict the polarity. Again, it's always just going to be an either or distinction for you guys. And that, the questions could be set up a little bit more complicated than that. You might have to figure out how many of the molecules are polar and do it more than one time. But at the same time, for each individual analysis you're doing, it's really just going to be a question of, is it polar or is it nonpolar? All right. And then let's just do another one that's exactly the same format. The molecular shape of IF3, the interhalogen compound, and its polarity. I know I have notes here, so I don't know where they are. I guess not. All right, we're going to wing it again. All right, so for IF3, we have to start with a Lewis structure. So we have iodine and fluorine in the formula. Both of those are group 7 elements. We did another interhalogen example last week, I think. So 7 electrons from iodine, 7 from each of the fluorines, different principal cloud numbers, but that's the total number of valence electrons is what we care about. So 7 from the iodine at the center, 7 from each of the fluorines. So this comes out to 28 electrons around the center atom. All right, so when we draw this one out, we're going to start with single bonds. Again, at the beginning, we don't know what the shape is. So we're going to just draw it randomly. It doesn't matter how you orient them at this point. Complete the octets of the fluorines. So each of those fluorines has 8 electrons around it now, 2 from the bonds, 6 as lone pairs. So 8 times 3 is 24, but our total structure has 28 valence electrons. So that means there's 4 left. So those are going to go on as lone pairs. So 1 on, or 2 total on iodine. Okay. So that gives us then an AXE notation that's AX3E2. All right, so this is one of the weird ones that has 5 electron groups, the ones that are a little bit trickier to get our head around sometimes. So with AX3E2, there's 5 total electron groups, so we're still going to have that trigonal bipyramidal arrangement that we had last time. But this time, 2 of those 5 positions are going to be lone pairs. Doesn't matter which 2 we choose, but they have to be on the triangular part. So we're going to put 1 there and 1 there, for example, and that leaves the rest of these as fluorines. All right. So this is sideways, but we call this geometry T-shaped. So that would be the name of the molecular shape, T-shaped. And then polar or nonpolar, as we said a little bit ago, with 2 or more lone pairs on the center atom, there's not an easy or cut and dry prediction necessarily. You have to think about each one individually. So for T-shaped, what we would have is this is the arrangement of the 3 atoms around the center atom. It's distorted a little bit by the lone pairs, but you can essentially think of these 2 dipoles as more or less canceling each other out. But then you have this third IF dipole that I'm oriented here is pointing towards left to right. That one does not have one on the opposite side to cancel it. So this molecule would be polar, right? So AX3E2 is a polar geometry. So again, with 2 lone pairs in the center atom, we saw examples that are polar and nonpolar. You have to think about each one individually to get it. I'll have a summary here in a little bit. But all right, that's the last example question I have. So does anybody want me to go over anything that I've covered today in more detail, or All right, so the very last thing then is, again, another summary table that this time, in addition to including the names and molecular geometries, also includes the different possibilities of polar and nonpolar. And again, if you're going to use this table to help you out, remember that this analysis is rigorously only true if all x's are the same. So if you have two different outer atoms, that usually makes it polar. But in this case, just in the more typical situations, all of your outer atoms are the same. All of those that have zero lone pairs are going to be nonpolar. So that's this whole column here. If they have one lone pair, they're going to be polar. And then the ones that have two or three lone pairs, you see that there's two each. AX2E2 is bent. AX3E2 is bent and polar. This one's T-shaped polar, but then these two are non-polar, so some of each. All right. Well, hopefully this will help you because again, most of them are either going to be in these two columns here, which is straightforward, and then just a few more for you to wrap your head around. So you'll see that in the upcoming assignments where we ask you to predict polarity. And again, your job is just to predict if it's polar or non-polar, nothing more than that. For at least for in the context of just molecular polarity. All right, any last questions? I guess you guys are ready to go, so I'll stop there and see you on Wednesday.
Thank you.